Okay, so today we're going to start, we're going to do a thin film clarification. I had so many questions on thin films last time that I feel like it's worth going through it again, and we have the time built into the lecture, so why not? So I'm going to have someone named Claire come explain it to you. No, I'm not going to do that. I'm going to explain it myself, and we're going to go through carefully. Now, if you totally understood it last time, and you did the homework, this will still help cement it in your mind for the exam. And if you were completely lost last time, often seeing something a second time actually helps quite a bit. All right? So let's look at it. Thin films again. And I realized I did it kind of out of order. I should have done Young's double slit and then thin films. Young's double slit doesn't have the phase shift that thin films do. Okay, so as I get through these thin films, it's just A is just going to explode, right? True love. Yes, okay. Okay, thin films, here we go. I think part of the confusion was I drew this. Right? I mean, come on. Perfect explanation of thin films. Let's go back and take a little more time and think about what that actually meant, okay? So what is really going to happen to a wave going through a glass slab? What is really going to happen? Well, to tell you that, I want to tell you a quick thing about someday you're going to work in a lab. You're either going to work in a lab or a clinical setting, probably all of you. And you want to be like, the James Bond of that lab, right? Requires some sort of affectation, something to make you interesting. And my recommendation is that you get one of these, okay? Look at it. Just walk into the lab. Just set that on your desk, okay? Then eventually somebody will ask you, they need a glass slide, they need a microscope slide, right? So, you just sit there. You need a microscope slide? Oh, sure. There you go, right there. See, it's a microscope slide dispenser. Silver-plated. That's right. I'm telling you. This is the stuff they don't tell you at the other schools. Okay, so now we have a microscope slide dispenser, the key to science. Here's our glass slab. Here it is, okay? Now, what really happens to the light in a glass slab? See, I can still see you. I see all of you. I'm crushing your heads like a nut, right? I can see through the slide. So the light goes through the slide. That's the point. So I made it sound like, oh, it's a line. No. Okay, light's a wave through the slide. 96% of what happens, 92% of what happens is light goes through the slide, as you know, okay? But what else happens just a little bit as the light goes through the slide? A little bit of light reflects. That's why you can look in a slide and you can see like a ghostly image of yourself, right? This is the answer Randy Yao, who I knew in junior high, said, like, if glass is perfectly clean, why can you see it? And it blew my mind, right? I was like, dude, that's rude. But now I know. It's because light reflects 4% or glass, a dielectric interface like glass reflects about 4% of the light that's incident upon it. So you can see a faint reflection. So at a dielectric interface, you get reflection and transmission. You get both, okay? So if it's glass, N equals 1.5, I'm just telling you without proving it to you, you get about 96% goes this way and about 4% goes that way. All right? So it goes in, light goes in, blah, blah, blah. Very exciting. And so what we're going to do is we're going to ignore amplitudes. Okay? We're not going to really worry about amplitudes here. If you watch the extra lectures I posted, those keep the full amplitude description because it's sophomore physics. They still may be useful for you. But why are we going to ignore amplitudes? Because they're about the same. Because what else happens? Light goes in, 4% reflects, looking good, 96% goes in. But then at this interface, also 4% reflects. If you run the numbers with electromagnetic theory, 4% reflects. All right? So what is 96% of 4%? To a theoretical physicist, 4%. Right. Well, it's 1. Everything's 1 to a theoretical physicist. But my point is, this is almost the same. 96% of 4% is like 3.96% or something. I don't know. I made that up. It's very close to 4%. So the two beams coming out, the first reflection, I'll call the alpha ray, and then the second reflection, almost the same. And then some of you very astutely asked the question, what about the next reflection, right? Because then you're going to get this, and then you're going to get this, right? Well, let's run the numbers. What's 4% of 4%? Right? 4% of something that's already very weak now. 4 times 4 is 16%? No, that's not how it works. 0.16%. 0.16%. And then that weak, pathetic 0.16%, 4% again, right? Like 0.05% is coming out. So 4%, 0.05%. It's weird. The first ray, the second ray, about the same. Third ray, gone. Basically nothing, okay? That's why we just think about the first two. All right? So this is all we drew, right, is those two. So I didn't draw this part. Maybe that was the confusing part. Yes, it is glass. You get 92% of the light goes through. Not 100% of the light goes through. That's everything going on. Let's see. And why do we have these reflections? Because we went from n equals 1 to n equals 5 to n equals 1. Right? That was all happening. Okay. Let's see. But now we got to do the phase shifts, right? To keep up with interference correctly, we got to do the phase shifts. So let me write it another way. I thought, hell yeah, here it is. When you reflect off of higher n, I tried to write this in a way that it was simple and unambiguous. Higher n, you get a phase shift of pi. Right? And it is implied, well, not implied, I have to say it, period. Lower n, delta phi equals 0. Right? So that's what we said before. I'm just trying to say it real simple. Don't think about n1, n2, greater, lesser, internal, external. Just think, if I reflect off of a higher index, pi phase shift. Here, going in does nothing. Reflected off a lower index. Going through does nothing, 0. So there's your amplitudes and your phase shifts. Oh, nothing, okay. When do you add phase shift? High to lower, low to high. There you go. Yeah, you texted that right before I said it. Okay. That's why in this case we get pi and 0. Okay. Now why isn't this thing all beautiful colors like we showed you with the crazy film thing that I turned and it changed color and the thing in Herstein Amphitheater? That's because what you can do is you can engineer these interfaces to be more reflective. Right now we only have like 4% of the light doing this. If we engineered them to be more reflective, you could get all the light causing interference and having optical effects and changing colors. Right? It depends on color. Another thing I confuse you with is the reason you get colors is you send in white light. And only some of the wavelengths reflect and some don't. We're going to do a sample problem like that in a minute. So we'll go over that part. But anyway, we're telling you just the basics. And you may say, well, can't you see a little bit of color on the reflection? And actually you can. If you get a thin enough piece of glass and the light is coherent enough, you can hold it out in the white light and you can see it. I can barely see it, I think, with an LED. Once I was teaching optics, and fluorescent lights are very coherent. Incandescent lights are not coherent. Okay? So I had a really thin piece of glass where this effect still held together, and I could see the fringes here under the incandescent or the fluorescent lights. And I said, look. And I passed it around the room under incandescent lights. And they're all like, what? I said, no, give it back. It's not broken. Look, there it is. And I gave it back to them. Right? So it depends on how coherent the light is. We're not going to get into coherence, but it's something you can actually, it occurs even for just a glass slide. You don't have to have a crazy art exhibit, although that comes out prettier. What does trans stand for in the first bullet? Transmit. Took me a second there. What is the phase shift when you reflect off the same end? You don't reflect off the same end. You get at a dielectric interface. There you go. You don't reflect off the same end. Let's see. These are good questions. We're really hitting the fundamentals now. What does it say in the first bullet after the point? Transmission. Transmitted. Right? Why is it? Oh, somebody wants. You're going to have to get to A if you want this answered. Why is it 4% of 4% for the second reflection? If it's 90%, the 4%, here, it's 100%. And you reflect 4%. Here, now, 100 minus 4, there's only 96 left. What is 4% of 96? Oh, like almost 4%. Now, this is 3.96%. And now 4% of 4%. What is that? Oh, that's nothing. Wah, wah, wah. Okay, so I'm just multiplying by 4% every time there's a reflection. All right. Okay, that's the basic idea. So if you understood this, you're fine. You're getting a little deeper. And now if you didn't understand that, maybe that makes a little more sense. Okay. So what are we going to do with that? Now that we have that, let's go back and we're going to just do the two cases again, constructive and not so constructive, and destructive. We're going to see what we get real quick. Now that we all agree on that, let me come over here. That's the new fast way I get across the thing. Okay, because on our bullets, I'm sorry I can't get to the printer. What are we trying to do? We're trying to use mathematical description of the wave. Right, we're calculating maximum minima positions. No. Oh, yeah, that's why I did thin films too early. Here, that's this week. That's why we started too early. Understand when to apply phase shifts on reflection of light at a dielectric interface. Right, that's what we're doing right now. Calculate thin film thickness and wavelengths for the constructive and destructive. That's what we're doing right now. So here we go. And I'm on the janky board here. Let's do constructive wavelengths. All right. Oh my God, I hate these boards. Let's just switch over here. And I will tell them to fix it. Okay. Okay, so say we have a film like, are you kidding me? A film like that. Let's look for the constructive wavelength. Right, the constructive wavelength. So we can remember, what are we talking about? We're talking about a thin film, right, of thickness T. Right, and some wave comes in and hits it, and we want to know what is going to be a constructive thing back. What you want to be is good at this with the basic formula. You don't want to memorize every case. Thin film, air on both sides, constructive equals this. Because you know that the questions on the exam will be some way that the formula won't work. Right? This is how we make sure you really know it. Why are you using 4%? That's the part I can't explain to you because it's electromagnetic theory. It's 4%. You just have to trust me. I will post like 2 hours of lecture that explains why it's 4%. Okay, so how do we get the phase difference? We say, well, we got to do our incident ray like this, like that. So I'm going to draw this a little different, and I'm going to call this incident instead of doing all the angles. Right? The incident comes in like that, and we know one of them is going to reflect somehow and going to come out, right? And then one, like we're going to have 1 and 2. Let's come back to this. Okay. So we're going to call them 1 and 2. So the difference of 2 minus 1 is what? So it's how far x2 minus x1, where that's kind of how far they went, the difference in their distance, over lambda naught. Remember, we're going to multiply it by the index n, because really the wavelength is lambda naught over n, right, times 2 pi, plus, so that's difference in path. Now we need the difference in phase. And what's the difference in phase? 2 minus 1. 0 minus pi. So I would write it like this, plus 0 minus pi. All right. Constructive. There's the path difference. There's the phase difference. Equals, what does it equal for constructive? 2 pi m. Right? It could be 2 pi, where m can equal 0, 1, 2, 3, la, 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 la. That's actually a phone call. Let's ignore that. How do I tell it to go away? Oh, no, sorry. Okay. Let's see. So we just plug some stuff in here. We say, okay, what does it equal? What is the difference in the path from one to the other? One goes through the film twice, 2t, and one doesn't go through the film at all. So the answer is 2t. 2t. You get that? One went in and back, 2t, times n over lambda naught. That's basically how many waves it went through as it went, right? The thickness divided by essentially the wavelength in the material. All right, times 2 pi minus pi plus minus pi equals 2 pi m. That's the physics, and now you do the math. You say, well, I'll cancel the pi's, I guess. And this minus what is now 1 will come over here and become 1. 2m plus 1. This becomes... I didn't cancel the 2 pi, I just canceled pi. So 4tn. 4tn over lambda naught. right, is 2 pi m plus 1. So we look at that, and we say, which m's? It's these m's, so it's still 0, 1, 2, 3, whatever. All right? So if we want to know what wavelengths, what vacuum wavelengths, I'll keep doing that, we'll have constructive interference. We just solve this for m. Or, I'm sorry, we solve this for lambda naught. M equals 0, 2 times 0 is 0, plus 1. We have 4Tn over lambda naught equals 1, so lambda naught. M equals 0, lambda naught equals 4Tn. What about when m equals 1? 1 equals 1, this is 3. 4 over 3, lambda naught equals 4Tn over 3. Cool. What about when m equals 2? Lambda naught, 2 times 2 is 4, plus 1 is 5. Lambda naught, 4 over 5, equals 4Tn over 5. Dot, 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 dot. All right. What does N stand for? N is the index of the material. Remember, what goes here really is the wavelength of the material in the medium, but we call it lambda naught over N. N. There you go. A little ballet for you there. How did you get 2t from x2 minus x1? This is how far x2 went. This is how far x1 went. I'm x1. Oh, I didn't go in the material. Now I'm x2. Da, 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 da. Oh, I went t. Oh, and another t. 2t. X2 went 2t farther. Will making it exciting help? Yes. No. Okay, I'll stop. One of the questions used that. Yeah, I don't know. Okay. Let's see. I'm not going to make it through the whole lecture. How do you know what m is? I'm doing all the m's. I didn't pick an m yet. They all have meaning. Okay? All m's are important. Okay. Now I'm going to tell you the difference of the m's. Okay? We're going to look at it graphically. Because you might look at this. You might look at this and say, now wait a minute. I thought the case of constructive interference was when it was like even integers here. Why is it 1, 3, 5 for constructive interference? Jesus. I can't talk right now. When is it 2t over n wavelength equals 1? That was for m equals 0. I plug 0 in here. 0, 4Tn over lambda equals 1. I brought the lambda naught up here. Right, equals 4Tn. All right? I'm about to just stop answering these so we can get a coherent story going here. Yeah, okay. La, 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 la. So now what I want to do is give you a physical intuition. That's the whole reason I'm doing this again. A physical intuition for why we have 3 answers and how they're different and what they mean. All right? Here we go. Here we go. This is when I meant to draw this more separated. Here, you have the incident wave. Let me draw it thinner here. Here's our thin film. Incident wave, like that. Okay, it's a sine. It's going in right where it wants to go up again. Okay? That's the incident wave. Now let's draw the one that reflected immediately. Number 1. Can we draw, this is incident, this is 1. Can we draw it? I don't know. Okay? It's going to reflect. It's going to go through a pi phase shift, right? If it didn't go through a pi phase shift, would it be up or down? It would be up because it wants to keep going up, right? But it did go through a pi phase shift, so it's going to be down like that. That's what 1 looks like. It doesn't look like a pi phase shift, does it? Well, I changed directions on you. It went down and back up. Oh, pi phase shift, down and back up again. If I were to draw this as a continuous sine, it would look like this. Whoop, whoop, pi phase shift. Okay, that's what that is really, I swear. Okay, let me get rid of that. All right. Stick to the notes. Stick to the notes. Okay. Now, number 2. Now let's look at the wave that went in and came back out. All right? Wave 2. Here we go. What is the relationship between the wavelength and the thickness? It's basically a factor of 4. You say, but there's an n there. Yeah, but I'd have to draw the wavelength shorter by a factor of n and it would cancel out. Okay? So when you're drawing something like this, you just say n equals 1, or n equals very close to 1. It's too hard to precisely draw the wavelength difference. Okay? But the point is that the thickness is a fourth of the wave. T is lambda naught over 4. So let's ask ourselves, what's going to happen to 2? All right? Here we go. There's no phase shift here. It's going to continue to go up. How far? A quarter of a wave. All right? It's going in. Quarter of a wave. When it reflects off the back interface, does it undergo a phase shift? No. 0 phase shift. How is it going to come back? Well, it's already high. It can't click to low. It's like this. Right? This is forwards. This is backwards. Right? And how's it going to continue? It's constructive interference. Thank you. Constructive, like curtsy. Constructive interference, okay? So that means it worked. That means when we put m equals 0, it worked, right? Now let's do m equals 1, because we're just on a roll. I am having a lot of fun up here. Okay, here we go. So now we're going to draw m equals 1 and see physically what is the difference. I mean, you know it's going to be constructive, because Hafner never makes mistakes. But what is physically the difference? Let's see what happens. Okay, let's look at this. Incident's going to look something like that. There's incidence. Right, okay. What is the reflected wave going to look like? 1, it's the same. The reflected wave doesn't care what m is. It doesn't care how thick the thing is. It's instead of going up, it's going to phase shift and go down. Exactly the same as before, right? Yeah, okay. 2, let's look at wave 2, the one that goes into the material. And let's look at the relationship here. The thickness is 3/4 of the wavelength. 3/4 of the wavelength. So what does that mean? It's going to go through 3/4 of a cycle before it hits the back. Okay, it's going to go up 1/4 of a cycle, 2/4 of a cycle, 3/4 of a cycle. 3/4 of a cycle before it hits the back, because t is 3/4 of lambda, not over n. Doesn't the wavelength change in the film? So I'll get to that in a minute. Let's finish. Okay, how does this reflect? No phase shift, right? It's very hard to draw. That's why I keep looking at my notes. This is hard to keep straight, okay? No phase shift. It's low and wants to go up. Okay, low and wants to go up. Let me see it. What does it look like? Oh, and then 3/4 of a cycle. Oh, my God. Look at that. Constructive again. Thank you. Let's see. Why is it 3/4 of a wave? Because we've got m equals 1. 2 times 1 is 2, plus 1 is 3. We put lambda over here and 4 over 3 here. So lambda is 4/3 t, but t is 3/4 lambda. That's where that came from, m equal 1. M equal 2, the only difference for m equal 2 is you would stick, now let's see, we put 1/4 of a wave here, then we put 3/4 of a wave here, you're just going to put 5/4 of a wave here. That'll be the difference. And then we could put 7/4 of a wave there, right? On and on and on. Now, why is 1/4 of a wave in there constructive? Right? If you have 1/4 of a wave, you go up and back, that's half a wave. They're half a wave out of phase. That should be destructive, right? Why are they constructive? I can't. What? Why are they? Oh, because there's a half wave on the reflection difference. Right? A half wave on the reflection difference means you need a half wave on the path difference. So it's sort of like what you think of as constructive and destructive kind of switched. Right? Because of the half wave reflection difference. Yes, yes. Why are there no phase shifts for the second one? That's just electromagnetic theory. Watch my 3 hours of lecture that I will post. You just got to believe me. It's called dogma. Okay. Let's see. I mean, I'm not trying to say, you know. Let's see. You all do know that it was called the central dogma of molecular biology because the guy didn't know what dogma meant, right? I mean, he would not have actually said, I am handing you the central dogma of molecular biology. It's because he thought dogma meant something else. He didn't think he was God or whatever. He's not a physicist. All the waves to the left of the film look the same to me. Is the difference between all the waves to the left look the same? Yeah, because it's constructive, right? We're going to do destructive in a minute. They look different here, though. All right. This is the new fun way to teach physics. Is there a phase shift? How do we know 1/2 wave reflection difference and why it affects path length? I can't quite follow that one. Okay, now let's do destructive. It's so exciting. If you didn't get it for constructive, it might click for destructive. We're going to just do the whole class on this. We'll do in between next. Deconstructive. Let's figure out for this film, deconstruct, not a word. Is that right? No. I made that word up. I'm so epic here. Does this formula only work for... Yeah, you don't want to memorize it. Does this formula only work for constructive with light wave entering a medium of a higher n? No. It only works for constructive for light wave of a medium entering higher N when there's lower N on the back. Right? If this were on glass and you had a higher N here, then they'd both have a pi phase shift. You don't want to memorize a formula for any case because it's going to be different every time. Okay? This will always work for like a soap film. How does N affect the shape? I'm drawing any shapes. I don't know what you mean by shape. The angle, yeah, remember when we draw angles, it's just so you can see everything. We're doing everything without an angle because that gets too complicated. Deconstructive lambda, here we go. Let's see if we can just do it mathematically now. The delta phi of rays 1 and 2, what's it going to be? The path difference is the same, right? Ray 2 goes 2t. 2t, ray 1 does not enter the medium, right? Times n over lambda naught, because that's the wavelength in the medium, times 2 pi. For deconstructive, what's the phase difference? It's the same, right? Number 2 had no pi phase shift, and number 1 had a pi phase shift like that. It's the same. Well, what's different? This. We don't say it's equal to 2 pi m. We say it's equal to pi m. And we say m, in this case, only equals the odd integers. So you could say, well, but it's physically the same. How's it a different answer? It's because we're asking different questions. What wavelength will be constructive off of this film? What wavelength will be destructive off of this film? Those are not the same thing. Okay? So we look at it. We say 2 pi, pi. Now it's just 1 pi there. So the pi's go away. This actually comes over here and makes m plus 1. Right? This 1 and this m plus 1. This becomes the 4tn. So that part's the same, 4tn over lambda naught, but now it equals m plus 1. Before it's 4tn over lambda naught equals 2m plus 1. But it's not for all m. It's just for, remember, m equals 135, yada, yada. All right. Can you also set it equal to 2 pi m plus 1/2 for all m? Yes. You can construct your odd integers any way you want. You just have to stick with it. Okay, if you make some fancy schmancy version of odd integers here, you got to use it when you get here. And this won't be the same. I know, yeah. The world is complicated. If it weren't, we wouldn't be here. Okay? If physics were easy, we would be hydrogen atoms just kind of floating around, which wouldn't be so bad. So here we go. Let's solve it for the longest m. The longest m would be the lowest m. I'm sorry, the longest wavelength. Let's see. What is the longest wavelength? We're going to get out of this. Lambda naught is m equals 1. So we're just plugging in a equals 1, right? So 1 plus 1 is 2, which makes that to a 2, and that lambda naught goes there. So it's lambda naught is 2tn over... Oh, that doesn't make sense. Let's see. It's just 2tn. Yeah, I was solving for lambda. It's 2tn. Right? We just 2 under here, and that goes there. 2tn. So it's different. Oh, thank God. It's not the same, right? It is different. And then m equals 2, I bet you could do it. It would be tn. And then m equals 3, 2tn over 3. Let's draw just the first one. And make sure it comes out constructive. And then we'll move on with our lives. Because we've got to redo Young's double slit also. Let's see. Destructive. Incident. Whoa. Okay. Incident wave looks like that. Reflected wave. All the same, right? Pi phase shift. Oh, crud. I need to draw them all the same here. I don't want to go crazy. Let's draw it like that. Wouldn't want that to happen. Incident wave 1 down, up, like that. There we go. Pi phase shift for number 1. Number 2 is going to go through the wavelength. Let's see. The thickness is half the wavelength. Okay. I think I can do that. Let's see. 2. La, 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 la. It's going to go in half a wave. It doesn't do anything here, so it's going to go like that. Right? This is going forward. Now it's going to bounce back. Is it going to have a pi phase shift? No. It's at a lower index. So to come back, it's going to go down like this and come out like that. Thank you. Right? Deconstructive or destructive interference. Right? It worked. Hallelujah. If you did the next one up, it would be a full wave inside the film. Okay? So when you get to these higher m's, you're often just talking about sticking more waves inside the film or the path difference to keep achieving constructive or destructive over and over again. And this kind of a problem, it's not just shifting the same wave, it's actually finding the different wavelengths that'll fit. Right? That's why these film problems are often asking for various wavelengths. Which one's bright and dark? It's because you've got to cram them in there. All right? Yes. Why is M135 for destructive? Because that's the only way to make it destructive. So we did that. Yeah. For constructive is the longest wavelength m equals 0. So do you use m equals 0? Very common question. Do you use m equals 0? Totally depends on the problem. Okay? Usually it's safe to plug in m equals 0 and see what happens. Okay? What would happen here? Let's see. Oh, I did use m equals 0, right? Sometimes when you use, what if that weren't there? And you plugged in m equals 0. What are you going to get for lambda? Infinity. Probably not the right answer. Okay? What if I'd have said, I want to define a pi phase shift as negative pi instead of positive? What if I wrote negative pi over there? This would come out positive. This would be dropped. All the numbers would be different. And then maybe you couldn't use m equals 0. So I wish I could give you a universal. But there is no universal. It depends on how you set it up. I could say, here's exactly how to set it up for all 38 cases. But I'm not going to, that would be annoying. We'd have to lecture for hours. So there's destructive interference for the second reflected wave, not the first. Oh, okay. Remember, you can only have interference between two waves. There's destructive between these two. So if you, I don't know if you meant by the first, you meant this, and remember, it's the between two waves is destructive. But yeah, that's constructive. This is destructive. All right. Why is one the same as the incident? Yes, go back and watch the video. Why is one the same as the incident? I don't have time to do that again. All right. Okay, so now I have a problem we can do. Let's do it real fast. Here it is. I'm going to let you look at it. I'm going to, I'll do it over here on whichever board I can get to behave. Here's the problem. This would be like a pledge problem, like an elemental version of a pledge problem. It's the worst word you could possibly have come out first in a physics question, show. Yeah. You don't want to see show. Okay, that's like the last thing you want to see. Remember, if you've done the homework yet about the diver or something like that, the scientist outside sees a positive, like a bright color. Where does the diver see a bright color? And we say something about conservation of energy. And if it's reflected, if it's constructive on reflection, it has to be destructive on transmission. Right? So let's see if we can show that. Show that the longest deconstructive, I've made up this word, I can't get reflected wavelength corresponds to the longest constructive transmitted wavelength for a 200 nanometer thick glass. Okay? So I'm not going to do it as slow and explainy as we just did for the other stuff, but let's just go through it. Because I think you're getting the feel for this. Okay? Here is our film. 200 nanometers thick. Index of 1.5. Very standard. Here we go. Wave comes in. What does it do? It goes right through. I promised you it would just go right through. Okay? A little bit reflects, and a little bit reflects here. So there we go. But we also now have to think about what gets through. We actually need to think about this reflection. All right? This is where we're throwing you a curve. We didn't tell you how to do transmission, but if I drew you that diagram on the pledge problem, you would be able to do it. Okay? So let's look at the deconstructive case. Let's do first what we know how to do, reflections. Okay? Let's say we just did this. Let's just do it again. Delta phi. We're going to call this 1, and as always, call that 2. What's the difference in path? 2t. We multiply by n over lambda naught, because that's the wavelength in the medium, right? Times 2 pi. Crud, I wrote too big. I need to move it over. And then we end up with minus pi here. Right? That's exactly what we did over there. Right? Because 0 phase minus pi phase. And we want it destructive, equals pi. I'm not going to write m pi because we want the longest one. The longest one will always be the lowest m. Okay? For deconstructive, you don't have 0. You just have 135. This comes to here, and you say, okay, well, that's 2 pi, and that's 2 pi. So basically, we've just got 2 times 200 nanometers times 1.5 over the lambda naught we're looking for equals 2 pi here, cancel them, it equals 1. Okay. So this is deconstructive. The longest wavelength is deconstructive here, 600 nanometers. The vacuum wavelength is 600 nanometers. Beautiful, right? Okay. That means that's that first case, right, where it's like half a wave fits in here, something like that. half away, but it should be 400. Oh, but it's n equals 1.5. Okay, so now you got to do the other case. Here, now we're doing new things. This is like you on a pledge problem. They didn't show us how to do this. It's not even in the book. I'm screwed. Yes. Okay, so let's do constructive on the transmitted side. Ooh, okay. What phase shift do we have here? 0. There are no reflections here, right? What phase shift do we have here? 0, right? This is at a lower index. Boom, 0. Lower index, 0. The whole thing is 0. Can you believe it? No phase shifts to deal with. Where did the m go? I said equals equal to 1. I talked very fast. There you go. I said because we're doing the longest wavelength is the lowest m, therefore m was 1. Okay, so let's just set it up. Maybe that's enough. Delta phi equals, what is the path difference between 1 and 2? Oh, the path they spend in the material. So you could say, well, 2 goes 1, 2, 3t. Whoa, and then but 1 goes 1t. All right, so there's your path difference. Index over lambda naught, that's what we're looking for. All right, and that plus the phase difference is just 0. Neither one of them has a phase difference. And we set it equal to constructive. All right, constructive. Constructive is 2 pi m. We want the longest wavelength. Does m equal 0 work? No. If I put m equals 0 here and I put a 0 here, I just get lambdas like infinity. That's no good. So it must be 1. It must be 2 pi times 1. Okay, so now, oh, I forgot my 2 pi here. Sorry. All right. So now we are cooking with gas here. The 2 pi's go away. That becomes 1. And this becomes 2t n over lambda naught equals 1. Lambda naught equals 2 times 200 times 1.5. What does it equal? 600 nanometers. Woo! Look at that. That's the same. All right. The destructive reflectance on one side equals the constructive reflectance on the other side. Technically, it's because we have to conserve energy. Okay. Someone asked, do you ever use m equals 0 for constructive? Maybe. It depends on how you set up your phase shifts. Right. Sometimes you have phase shifts in there, and you got to use m equals 0. So I recommend just trying it. Like I just did. I said, oh, if m equals 0, then we get a nonsense answer. Okay. All right. Woo! Who's tired? Wow. Good. You should, yeah. Hard to listen to, I know. Okay, 5-minute break then. 10:04. Look at the wall. Wow. Okay, so I'm going to regret it, but we're also going to clarify Young's double slit. Why not? One board with everything that you need for Young's double slit. So I think it's worth it. All right? And I figured out a way you can actually see it. I'm using you as guinea pigs, basically. Okay, Young's double slit's actually a lot easier than thin films. That's why in our description of the class, I said we would do it first. And then last week, I don't know. I don't know what happens. We got to be a little spontaneous, right? Double slit. I think the physics of it you get is just I totally over-explained the approximation to the point of ridiculousness. And I like to keep it, classy here. So Young's double slit was a plane wave comes in. Where it goes through the slit acts as two point sources. So you say, okay, a wave goes here, and a wave goes here. And you say this is like the origin. So you want to know where do you get light, constructive and destructive, along this y-axis that we call the screen. Right? You literally project light onto the screen. Right? And we know what happens because we have one here. Here it is. The light is a little plane wave that's going to show up right there. Ooh, there's a plane wave, right? And I'm going to drop a double slit in there. And I even have a picture, a microscopic image of the double slit. There it is. In this little film, duck, are two little slits the light's going to go through. It's going to go through two little slits. Don't you think you're going to see two little slits up here? All you classical geometrical optics people? No, you're not. So let's put it on there and see what we get again. Remember, how could this possibly happen? Oh, say it ain't so. Here it comes. La, 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 la. Ooh, wow. It didn't show up. Okay. There. Oh, look at that. Did we get like an image of two slits? No, we got this big repeating pattern like this. Whoa, look at that. Why did it do that? Surely he switched the slits. He's got one in his pocket that looks like that. Well, I would do that, but no, I don't. I don't really have that. Look at that. And now, ready? Watch this. Oh my God. There it's back. Look at that. There it is. Ooh, I'm enjoying this too much. How do we get that pattern? Right? How can we possibly describe that? All right, so real quick. The reason is we go from places where it's constructive to destructive, constructive, destructive, constructive, destructive. That's all it is. And we can use a formula because we know the difference in the path is basically right here. This is delta x. And it's equal, if this is d, this is what we said last time, equal to d sine theta if this angle is theta. Right? Because there's your right triangle right there. The difference in path is that d times sine of this angle. And this angle contains the information of how high you are along the screen, because you know how far the screen is, and you know the angle tells you how high you are along the screen. That's what we were doing last time. So if we did the interference case, we'd say, okay, delta phi is the difference, d sine theta, over lambda naught. There's no index to deal with. There's no n. We're not going into a dielectric here. Times 2 pi. What's the phase shift? 0, right? It's two sources, and they're in phase because they're coming from the same light source on the back. So there's nothing there. We want that equal 2 pi m. Now, would you ever use m equals 0? Here's a case where you would. What does m equals 0 mean? It means they are going the exact same path length. Where do they go the exact same path length? Here. Right? So here's a case where you would use m equals 0. Right there. And you would probably get a big constructive interference there. So m equals 0, 1, 2, 3, blah, blah. The next time it's constructive would be, I mean, I could pretend it's happening right here. M equals 1 right here. Right? So you get a big positive here and a big positive there. Now let me show you real quick what all the crazy approximations were. So here's your slit. In the real world, the slits, you saw I'd use a microscope to show you. They're less than a millimeter apart, and this is like 10 meters. So it's a very small angle. I'm going to exaggerate it again just so you can see it. But what really happens is if you go to some position, this is theta. So so theta is very small and roughly the same for all paths. Right? That's the idea. You can tell clearly these two are not going the same angle. Right? But if you make that angle, if you make this really far away and the angle really small, then they're going essentially the same angle. Right? So there's one approximation. Because if we make that approximation, then let's solve this. So 2 pi, m is here. We get d sine theta equals m lambda naught. All right, so that's kind of the main case for when you have constructive interference, where you're going to get the bright spots in the pattern. Right? But now we want to do approximations for the height on the screen. So we just say, what is sine theta approximately equal to? So here it is. Don't worry about tangent. Just say this. What is sine theta? It's opposite over, the hypotenuse, not the length L. Damn. Right? It's y. It's actually not approximately equal to y over h. It's equal to y over h. But it's approximately equal to, what is h roughly equal to? L. Right? This is so low, h and L are basically the same thing. Y over L. Right? If you say that, then you say, okay, I'll just stick this in here. That's what he was doing last time. Y over L equals m lambda naught. So this is the simple geometry where you don't even need to use angles. As long as you're far away, which you always are, then you just get, this leads to what the final answer last time, y m lambda naught L over d. All right? And do you use all your m's? Yeah. So here's m equals 0. Here's m equals 1. Here's m equals 2. Here's m equals -1. And then I gave you the formula that shows it really does this. All right. So that's just everything you need for one board. Basically, if you're asked a question about angles, you got it here. If you're asked a question about height on a screen a distance L away, you use that. How could we possibly make that tricky? Oh, we have ways. How does mode affect y? So the different modes, so physically what's going on, m equals 0, they're going the same distance. M equals 1, that first maximum you get, basically there's one wave here. All right, so they would be constructive. This one goes farther, but if it goes farther by one wave, then they're constructive again. M equals 2, 2 waves fit here. You can say, but there's only one wavelength, but as I raise this height, we're getting more and more waves in there. Okay? Even though it's a small angle, this is really big compared to the wave. I mean, the wavelength is teeny, and this difference is teeny. Remember, they're both teeny. So they both kind of are about the same. Why do the modes result in different height? Yeah, so that's what I just said. You have to increase the angle to fit 0 waves, 1 wave, 2 wave, 3 waves. That's why it takes different heights to fit more waves in there for the different cases of constructive. All right? So I don't want to spend like tons of time on that. Would the first destructive be m equals 1? I believe the book said otherwise. Destructive, you'd have to put pi here. Who knows? The book might have found m funny. If it doesn't match, we'll talk about it later. Like I've said a few times, you can't really have some universal, this is how you treat m, because it depends on 100 things. Right? So it may not look like it matches the book, but it does. Okay, so now we look at this and we say, okay, well, that's brilliant, but what about why does it not do this forever, right? What is really going on here? Like it's here, and then it goes away, but then it's back. Look at that, it's back. And what if we look higher up? If we got it really dark in here, you could see it keeps going really high. Oh, look at that, I can see it right there. Look at that. It keeps going forever, and it kind of comes and goes and comes and goes. So why is it not just the cosine squared I told you about last time? Uh-oh. I broke my toy. Here we go. Let's see. It's not that one. It's that one. There we go. Okay, so let's think about why. Let's do another amazing blow-your-mind demo of it. And then I can turn this off. Okay, so we're going to look at another thing. We're just going to put one slit. So with one slit, how could you possibly get interference with just one slit? Oh, I had a picture of the slit, and it's gone now, so I don't know where it is. So here's the single slit, right here. All right, so it's basically two razor blades coming together. See, it looks, you can kind of see it's a slit. And this knob lets you adjust the slit. Ooh, this one is adjustable. Okay, so we're just going to drop this slit into the beam and see what happens. And if you're a big fan of geometrical optics, you'd say, well, I'm just going to get like a narrowed slit. Right, that's all. Yeah, there it is. Huh, that's not so exciting. Okay, so let me start narrowing the slit down, and we'll see what happens. Am I narrowing it? Oh, whoa. It got longer. Why when I narrow the slit does it get longer? Whoa, what is that? Look at all those extra peaks. It's just a slit. What? Ah! So I'm getting narrower and the slit is spreading out further, right? Very weird. So now we've got to figure that out. Ugh. It's never over, is it? No. No. April 20th, it's over, but yeah. It seems like it's never over. So to figure that out, we have to transport ourselves to Leiden in the Netherlands, University of Leiden, Netherlands. 17th century, right? And a young physicist named Christian Huygens. Kind of a pretty boy. Here's Christian Huygens right here. And he figured out a way to deal with this, okay? Now remember, it's the 1700s, or no, it's the 1600s. So we didn't have like, fancy math to figure all this out. I don't need the whole, I need a foot. Can I have a foot? No. Screw it. Oh, okay, I got it. Okay, here we go. Okay, so Huygens figured this out, okay? So he said, he's like in his dorm room, freshman year, getting real philosophical, right? And he's like, dude, like everybody's trying to figure out how does a wave propagate forward? Like, how does that even work? They didn't have math to describe it. It just seemed like a wave propagated forward. We draw a plane wave like this. We just draw these lines. Oh, it propagates forward. E equals E naught sine kx minus omega t plus phi. He'd say, what's that witchcraft you're saying, right? He doesn't know. He said the way it propagates forward is, here he goes, each wavefront breaks into spherical wavelets. And those propagate. What? Wow. And he said, what if the whole universe is like an electron in another atom? He also said that. Right? That's where that comes from. So he said, what's happening is this is breaking into a spherical wavefront, right? And then you propagate those. And then this is where the lack of mathematics becomes a problem. He said, basically, you draw a line that kind of follows those. Like that. Propagation. Christian Huygens, 17th century. Let's see, what did it explain? It actually explained diffraction, kind of. Okay, because here you've got, everybody's wondering, why does the beam spread after it goes through the slit? Well, when you go through the slit, now you're limited to less points. Right? You've only got 3. So let's propagate those. A little bit longer, a little bit longer. Right? And let's look at, what do we draw this wavefront? Ah, look, it got curved and it's kind of going out because some of them are missing. And it's going to go like that. Right? It's going to spread, just like we just saw. As you pull this together, the wave spreads, right? As slit narrows, waves spread. Right? So this little geometrical idea seemed to explain things in the 17th century when all you had to do was draw stuff. Not a lot of field theory going on yet. But it doesn't really solve everything. Okay? We can't really solve a diffraction integral. We can't explain those wavy parts with just that. Right? We need more. So his roommate was Augustin Fresnel. All right. Okay, not really. His roommate lived 200 years later, but let's just give it to me. Okay, 200 years later, his roommate says, "Oh, but you got to consider interference between these things. You don't just draw this line. You got to think of this as the interference between all those points." Right? But there's a lot of points, right? There's infinite points. So what do? We can't. It's not double slit. It's not triple slit. It's infinity slit. What a nightmare. Yes. So we're not going to deal with a nightmare. Well, we're going to partially deal with a nightmare. Here we go. There's a trick we can use. Okay, Fresnel. Okay. So we call this the Huygens-Fresnel principle. All right. Let's see. Often abbreviated, the HF principle. By me. E. All right. Huygens-Fresnel principle is how we treat diffraction mathematically. Okay, so we're going to do sort of a simple version here. All right, so here's our slit. We'll put a few Huygens-Fresnel wavelets in it. All right, so here's our little wavelets that the plane wave breaks into. And let's say let's just look forward. Just straight, right? Straight. No, we're not looking at an angle yet. We're saying, does any light go straight ahead? So you say, okay, we don't actually draw Huygens' little circles. We just draw lines like this. And what you really have to do a diffraction integral is you integrate down the slit. All right? You add up an infinite number of little Huygens wavelets. The world says Huygens, I say Huygens. Wavelets, and you use an integral to make them. It's pretty cool, right? Yeah, it's a lot of fun, but we're not going to do it. It's not that much fun. But if we were to say on this case of moving forward, is all travel what kind of a distance? The same distance, right? All these just go from the slit to the screen. Okay, what's delta phi? The phase difference between any two, 0 over lambda naught times, there's no n, times 2 pi, plus the difference in phase. They're not reflecting off anything, nothing's happening. Splitting into a wavelet doesn't do anything, equals 0, right? So the phase difference is 0, so it's constructive. I won't put that there because you're used to finding a condition. I'll just say calculate that. 0, constructive. All right. So that's why we say theta equals 0 is and we call it the bright central maximum. Okay, so we can't do this mathematically. You just have to trust me. If you did the integral, you would get the brightest spot right at 0. Okay? But you can kind of physically tell why. Everything's constructive there. So the pattern looks kind of like this. Most of the light goes there. All right? The central maximum. All right. Now we want to do more, but we don't want to do a diffraction integral. So there's a trick to figure out where the first minimum is. Okay, let's look at the trick to find the first minimum. Yeah. Okay. All right. First minimum. Oh, no questions about this, or I've worn you out. You're just begging to leave. 1, 2. Okay, so here, so let's now consider the first minimum. Okay, so what do I mean by that? I mean like the pattern, you go from the central maximum, where does that central maximum end? So let's draw it here. And now what we're going to do is we're going to draw 6 wavelets here. 1, 2, 3, 4, 5, and 6. There. I'm going to number them. 1, 2, 3, 4, 5, 6. Really, there's infinite number. And we use an integral, but let's just for now pretend there's 6. And let's say they go off at some angle, like this, to a screen that's actually really far away. But of course, we can't draw it really far away. So the question is, at this angle, theta, so what theta is deconstructive? Is what we want to solve, right? And the width of the slit, we don't call it D because it's not 2 slits separation. We call it A. Okay? So for double slits, we want the spacing, we say D. For single slits, we want the width, we say A. Okay? So you might say, well, I don't know, it's just these two. Do I use D for A like in Young's double slit? But you have 2 that are spaced by this much, but then 2 this much, and then 2 this much, and then these 2. And we only calculated Young's double slit for 2 overlapping waves. We haven't done like 6 overlapping waves. So what do? Here's a little mental trick you do. Consider first minimum. Consider the wavelets in pairs spaced by A over 2. Ah, look, here's a Young's double slit here, 1 and 4. And here's a Young's double slit, 2 and 5. And here's a Young's double slit, 3 and 6. Brilliant. I just came up with that before class. It's really a great idea. No. It's in the book. All this is in the book. Okay, so let's draw 1 and 4. All right, so 1 is going off this way. 4 is going off this way. 1, 4, and this is A over 2 is their separation. Right, 1 and 4, A over 2. Now it does look like Young's double slit. What is the angle where that thing is minimum? Let's see. So the first minimum is going to occur where 1 and 4 is destructive. And you can see if 1 and 4 is destructive, then 2 and 5 is destructive, and 3 and 6 is destructive. Like they're all basically the same then. The same angle, the same spacing. That's why we're doing this trick with A over 2. All right, Young's double slit. Where's the first minimum? I think somebody asked that, and I said we will do it. Here we go. It's, let's see, delta phi. The path difference is there. Before we called that D sine theta. Now we call it A over 2 sine theta. Right? The path difference is A over 2 sine theta. So we say A over 2 sine theta over lambda naught. There's no index. We're just in air. All right, times 2 pi. What phase shift do Huygens wavelets have? 0. That part's easy. plus 0. Phase difference, phase constant difference. And now we want it to be we want destructive interference. I'm just going to, deconstruct is just a word. All right. We want destructive interference. So we put pi here. The first one will be at pi. 1 pi, 3 pi, 5 pi. That's when they're half a wave out of phase. Remember, pi is half a wave. Right? So at 1/2, not 2 halves, because that would be a full wave. It's got to be 1/2 of a wave or 3 halves of a wave. So we set it equal to pi, and we say equals 0, that's 2, oh yeah, the same thing. And we get that then the pi's go away, and wait, what have I done here? M equals 0. Wait, this has to be, oh yeah, this is a 2. Oh, that's a 1, that's not a 0. Whew, okay. Let's see, so that cancels, this 2 cancels that 2, and you get A sine theta equals lambda. So this 2 canceled that 2. A sine theta, and the lambda went over to the 1. Not. Right? So that's the condition where you're going to get the first minimum. When sine theta equals lambda naught over A. Lambda naught over A. All right, the first minimum. Okay, now why is that important? That is important because the main thing that we would ask you about this stuff is how wide is the central maximum. Okay? So let's look at a pattern now and see what all we've figured out. All right. Let's see, what have we learned about diffraction patterns? And if you remember when you looked at it, when it was spreading out, that big part was really bright, and the little wings weren't nearly as bright. What's the difference between A and D? That is just a tradition. All right. D is a separation between two slits. A is the width of the slit. Before, if I drew it, I drew D as like, here's a slit, and I was drawing between the two slits for D. Now there's only one slit. It's the width of the slit. Let's see. Okay, so the main thing is to show the pattern at the end, right? Okay, so the full solution of the diffraction integral. I'm just going to draw it. Well, I drew it once already. Okay, so say we've got a slit here of width A. All right, sorry, this drawing is getting shitty. Okay, here we go. There we go. There's one you can actually see. Some of you. All right, and now what are we going to get on the screen? What's this big thing called? Get your vocabulary going. The central maximum. And it goes to 0. And then it actually does that, right? Big central maximum, and then the peaks repeat, but they get really small. Okay? The central maximum will show up in one place, assuming you have like the axis where you would normally want to put the axis, is at y equals 0, right? If we think about the y position along the string, or it's at theta equals 0, right? It is straight ahead, okay? The first minimum where is it? It's right here, here and here. All right, this is the central max. Okay. And the first minimum is at y equals, if we make our small angle approximation, it would be at let's see, so this is, let's see. So we got to say, to find it, we take our other formula for, where was it? It was here, when sine theta. But then what is sine theta? We use the same approximation as last time. It's y over L, right? When sine theta is y over L, approximately equal to y over L, just like for Young's double slit. So you say y over L, how high you are, and y over how far the separation is in L is basically the angle. Right? And we set that equal to lambda naught over A. So this is the minimum. I mean, that's what we've labeled it, right? So then y is equal to what? Lambda naught L over A. All right? So that is where the minimum would hit in y. Okay? So what have we learned? Central maximum at 0. This is right here. These don't go together. First minimum, it's at lambda naught L over A here, and negative lambda naught L over A here. And that will tell you how big the central maximum is. Like for a lot of problems, that's the game of the game. How wide is your central maximum? How wide is it in angle? Here, you could take inverse sine of that and get the angle. That'd be half the angle. You might want to double it to get the full angular width. Or if you want to say how big is it on a screen, well, it goes from the maximum to 0 at this height, lambda naught L over A. Make sure I'm not saying that wrong. Or if you wanted the full width, it would just be 2 lambda naught L over A. Right? So the main thing we care about is where do those, how big is that central maximum? Because most of your light is in there. So if we were doing like a Young's double slit combined with this, you could say, well, like the Young's double slit would kind of like have a pattern like this. It's being modulated by the diffraction. And that's why we would see a bunch of peaks for Young's double slit, and then nothing, and then a few more peaks, and then nothing, etc. Okay? We'll talk about more on this when we get to imaging. This is the reason you have diffraction-limited imaging, but until we talk about imaging, there's not much point in doing that. And then I didn't get to gratings, but I can do gratings in like 5 minutes Thursday, so it'll be fine.